you think of him then as the early 1700s. They were both contemporary also with Halley of Halley's Comet. So one of the principles from physics that Hooke discovered is that if you associate a variable force with stretch or compressing a spring, something that's ordinarily elastic, and you don't stretch it so much or compress it so tightly that you distort the spring so that it can't spring back to its original length, then that force is proportional to the distance that you have stretched or compressed, it wouldn't matter, from what would be its natural length. The natural length is the length it would have if you don't have any force applied. So in my sketch, thinking of something, say, for example, that might be vertical, I have the spring just hanging here, with no weight attached or nothing pushing it the other way. So then if I compress it by an amount x from what was the natural length or equilibrium length, if you want to say it that way, then the force is proportional to this amount x. In the same way, if I stretch it by an amount of x, for example, if it were hanging here and I hook on a weight and let the weight pull it down, that would stretch it by an amount x. And again, the force is proportional to the amount of the stretch. If you've taken physics, you're familiar with this. So we're assuming that x and the force that is associated with either compressing it or stretching it by x act along the same line, which is vertical in the picture, or at least along parallel lines. If you're thinking of something where you hook on a mass and then because of gravity there's a weight and therefore a force, you can think of gravity as acting not just on one line but on any number of parallel lines, because it shouldn't matter where I walk here in the room, my weight should be the same because it's the same gravity. So Hooke's law then is that the force is proportional to the amount of stretch or compression from equilibrium. So this proportionality constant is what we call the spring rate, and people use that, for example, when they're in a car alignment and suspension shop. You can talk about getting a car with given handling characteristics and changing the higher rate springs to make it a stiffer handling car and less body roll and so on. So people that make cars really talk about spring rate in that same sense. So the units in this country are often going to be pounds per inch or possibly pounds per foot, and the metric units are newtons per meter. A newton is not a very big amount of force. It's about a quarter of a pound. In other words, it's about 4 ounces. So it is, I guess, what it is. It is something that to me doesn't seem very natural. It seems to me a unit of force ought to be bigger than that, but that's what it is. What I have seen said is that if you take a kind of an ordinary sized apple, see, that's the comparison with Newton supposedly being beamed by the apple, to think of gravity, and you hold your one hand up as high as you can, and you hold your other hand out in front, you let the apple go, and what this hand feels when it catches the apple is supposed to be about a newton. Okay. So anyway, work in physics is force times distance, but there's a little bit more to it than that because force and distance are both vector quantities, so there's a sense of direction and of magnitude. So what you're saying is that it's a force times distance product so long as you're measuring distance along a line parallel to the line of action of the force. And this again is how you cover yourself when the force is what we call a field, like gravity, where there's a force here and a force here and a force here and a force there, and so on. So when F is variable in magnitude, then your differential work would be the variable force dx, again assuming that the dx and the force are measured along the same or parallel lines. And then you can say that your work is your integral, which is where we're coming in on the homework, of course, from somewhere to somewhere of the variable force integrated along the line of action or a line parallel to it. So if you're in metric units, work is in joules. Joule was a French physicist. And if you'll notice in the development of physics and kind of the history of it, that people in France and England kind of vied with each other to name new concepts after somebody from their country. So we have the ampere, which is French, for example. We have the joule. We have the Newton of force, which is English, so on. Then the Italians got into it with volta and the volt, and the Germans got into it with the ohm. But anyway, most of the things are, that at least as we see them in this country, are either French or English origin. So, problem one, finally. Enough physics here, and you got to do something, even if it's wrong. Well, I got to tell you that story. My first job out of college long ago was with the company that now calls itself Exxon. They had a different name then. But anyway, I worked in Venezuela, and the first thing I learned was that their unofficial company motto anyway was do something even if it's wrong. So it's was an interesting place to work. So anyway, we want the spring rate, as we call K, when the work is 1,800 joules and the corresponding length of the spring, the natural length is 2 meters and you stretch it to 5 meters. So the question is, what's the spring rate if this much work will stretch the spring from 2 to 5? So you're going back to here, you see. You know the number value of the integral then, and the limits should be according to Hooke's law, where you're talking about the stretch from the natural length to whatever the length has become. Well, the natural length was 2, and you stretched to 5, so you've stretched really by 3 meters from the length it would have if you didn't have any force on it. So your limits on X, remember, are measured from equilibrium, like this. And so you have 0 to 3, kx. Okay, you integrate the kx, and you have a half kx squared, 0 to 3. And so that gives you 3 square, which is the 9/2, and the K. So then you can solve this equation for K. So 2 times 1800 is the 3600 over 9, and so you have 400 newtons per meter as your spring rate metric. In the book, you'll see that some of the problems want English units and some of them want metric units. So whatever way the problem is stated, then that's your clue to answer using the same units. So if it's given with joules, that's your, and the length's given with meters, you don't want to waste your life trying to convert to English units, just answer with the metric unit. So problem 3, the force is 2 newtons. If you, the book is using capital N for newtons. Yes.
6.5 Is it integral from 0 to 3 because?
Well, you see, the length was 2 meters,
Okay.
and you're stretching it to 5. And so I'm taking this as being the natural length. So the force, 2 newtons, will stretch a rubber band 2 centimeters. Now, the system that goes with work in joules is the so-called MKS, meters, kilograms, seconds. And so the unit of distance then that would go with meters and with joules would be, well, that would go with newtons and with joules is the meter. So what you have to do is change the 2 centimeters to 0.02 meters. One of the annoying facts about both physics and chemistry is you have to worry so about keeping your units right, so on. So again, assuming Hooke's law, our force has this type. And so what we're going to get from this information is our spring rate, because we're saying that the the force, the 2 newtons, is the spring rate times the stretch written in meters. So you can solve this for K. The 0.02 is 2 times 10 to the minus 2. So then you get 100 newtons per meter. And then you can answer the second part of the question. If this is your spring rate, then 4 newtons force will stretch by, again, your F is Kx, your 4 is your spring rate, which we've just found in the A part, times the x, solve for x, so 4 over 100 meters, or 4 centimeters. So then the work to stretch from natural length L to L plus 4 would be like this. Work is 0.04 meters. This is 4. This is supposed to be centimeters. Maybe that C doesn't think very well. And that looks more like 4 centimeters, maybe. So anyway, making that into meters, your limits on your integral are from 0 to this in meters. This is the spring rate, Kx dx, so you integrate that out and you get 0.08 joules. Okay, then the section 6.5 has some other kinds of problems. Not everything is Hooke's law here. In problem 7, and again, if you happen to have your book, you can follow by looking at what it says and their pictures. So they're talking about somebody who's up on a cliff, and they have 50 meters of what the problem calls rope hanging. Well, the only problem I have with this, first of all, a Newton, as we've said, is not very much. It's about 4 ounces. So then you take essentially 5/8 of that, 0.624, and so this is something that's an ounce or two for a meter of length. Well, that's hardly what I'd call rope. I think it would be all right to say line or something, but it's really not very heavy stuff at all. Well, never mind that. So how much work to raise 50 meters of it, assuming it's a vertical pull? So you can set these problems up in more than one way, but one way anyway is to let X be the amount that's hanging. You see, you're pulling it up, so you start with 50 meters, but as you're pulling it in, you don't have 50 meters out anymore. So your force that you're dealing with, which is the weight of however much is still hanging, is variable, and it's decreasing as you pull this in. This is a little bit like a ship with the chain and the anchor, and as you bring up the anchor, you still have the weight, fixed weight of the anchor, but the chain is very significant, and that's being wound around the thing on the ship that the anchor chain winds around. I think it's called the capstan, if I'm not mistaken. And the chain can be really quite significant in the weight, so therefore that force is variable. So the weight that's hanging, if X is the number of meters of line that are still hanging, then would be 0.624X, and that would be your force. And then your work would be the integral of the variable force times the distance, as long as they're measured along the same line as is required, since these are vectors. And the number would factor out, and so you have an easy integration and put in the limits, and you'll get 780 joules, which is what they say it is. You can do these problems more than one way. You can do it like this, where X is the amount that's hanging. The other way you could do it is X could be the amount you've lifted, and then 50 minus X is the number, the amount that's hanging. And you'll get the same answer if you do it that way. So, problem 8, if you read the story, you see the words lifted at a constant rate. The story has a bucket or a sandbag, I guess it's a bag, and the sand, it has sand in it, and the sand is leaking out, and you're raising it. Okay, so lifted at a constant rate, and then also sand is leaking at a constant rate. The two of those, where it's the word constant is in both parts of it, combine to tell you that the weight of sand that's remaining in the bag and the distance that, so that if Y is the weight of sand remaining in the bag, and X is the distance that you have raised the bag, then the Y is linear. You wouldn't know that the relationship between how much weight is still in the bag and how much you have lifted the bag is a linear relationship as opposed to a square or sine of or whatever you might dream up. You wouldn't know it except that they have to tell you somehow. And these are the code words to know that it's linear. It's because you're lifting at a steady pace and it's leaking at a steady pace, both. So what you get then is a situation like this picture for problem 8. Say your weight y of x that's remaining, you plot on the vertical, and the amount you've lifted from the start you plot on the horizontal. So the relationship is what would fit this line graph. That's the most challenging part of the problem, really. Quite often with these physics type problems, the challenge part isn't really doing the calculus, it's the physics. It's reading the story and getting what they really want you to do. So you see what you have, if you assume it's a line graph from the story, is 2 points on the line. When you start, so your lift is 0, you see. The weight that's in the bag is 144 pounds, as the story says so. You have it in front of you. Then it says, when you have lifted 18 feet, so now X is 18, half of the original is gone. It either says it that way or it says half is remaining. It's the same information. So what you know is the second point on the line is 18, 72. So lift, remaining weight. And so then if you know 2 points on a line, you can get the slope, right? Rise over run. So this minus that is the rise. And you notice it's negative because your slope is downward. And this minus that is the run. So what you're doing is you're losing sand at a steady rate of 4 pounds per foot that you're raising. And of course, if they had simply said that, you'd be at this point and wouldn't have to do all this. So you know the slope y-intercept form of your line. This is math 25, I guess. mx plus b. So just put in the numbers and you can factor the 4 if you want to. So then your work is your variable force, you see, which is the weight at any time. And they say how much work to lift the bag that far, and that far was 18 feet in the story. So 0 to 18, force times distance. And you integrate that, and if you don't happen to have a calculator with you, which I didn't, you can factor out the numbers, and then pretty soon you're multiplying 24 by 18, which isn't too hard. You get that many foot-pounds. If you have a calculator, you can check me, but I think you'll see it's right. Yes?
How did you figure out the work so if the bag was 18 feet? You just solve for X?
Oh, in the story, it's from the wording in the story. It's telling you that after it's lifted 18 feet, there's either half of it gone or half of it left.
Okay.
And then it says how much work to lift it that far, doesn't it? It's in the wording of the story.
Okay, thank you.
You wouldn't have any way to know otherwise. You notice then that according to this, it would be empty when you got out to here, which would be at x equals 36. So that's where the story would end anyway. Okay, so then what they call a particle in a physics class is something that will have mass and very possibly a velocity and acceleration, but it's supposed to be so small compared to what else is in the problem that you can think of this mass as concentrated at a point. So if you were thinking of astronomy, then you could think, compared, say, with the sun and how far away the sun is, you could think of the Earth as a particle, even though our vanity rebels against that. We think we're quite a bit and that the Earth's quite big. And it is if you're walking in the winter, but still compared to the sun or how far that is, it fits the definition. So what I'm trying to do here is talk about physics a little bit in these problems, because the book just assumes you know all that, but unless you've taken physics, you wouldn't. And so a particle can have velocity, acceleration, and therefore forces, such as force fields, which of course we're in, as the Earth, and the sun's force field, and so on. So then problem 10 talks about a particle that's along a line, and there is a force that's moving it proportional to 1 over the squared distance from an origin here to a location X where you would be. And you're assuming this force is acting on a line, as an electric force would, or magnetic or gravitational. Okay. So that kind of force, where the force is proportional to 1 over the squared distance, is the kind of force field that gravity is and that electromagnetism is. It's a very special type of force field that is important because we live in such a thing. So the work to move from some point, x equal b, to some other point, x equal a, is the work that we're supposed to calculate. So it would be from where you start to where you're going. You see, I'm thinking of this as if it's a force of attraction. Then our integral from start to finish, the force rewritten with the negative exponent times the distance dx measured along here. So you add 1 to the exponent and you get x to the -1 power over -1, so you get minus k over x from b to a. So then put in your numbers and simplify, and you get a formula like that. So there's an issue of sign, plus or minus, in something of this kind. And this is really an issue of definition. Usually work positive is done by the field, if you're thinking electromagnetic or if you're thinking gravitational, and work negative is done against the field. So when you're talking gravity problems, usually you take positive down because that's the way gravity pulls. And so if I pick up a second here. get me another high-priced mathematical model. Okay, here's the 12th edition of the book, and say it weighs 5 pounds, and if I lift it 2 feet, I have force 5 pounds times distance. So typically, if I lift it like that, that'd be -2. If I let go, then that'll be plus 2 times 5. So minus would be up, and plus, say, then would be done by gravity. And you notice that the total work, if you think of, again, the minus being up, and the -2 times 5 would be -10, and then I let it go, and that's +10, so then the total on the closed path will be 0. That's true for something like a gravitational field. If you take third semester calculus, we do a lot more of work with the concept of a field and what's called a conservative field, like gravity, where you do the work one way and you get a negative value, you go back and you get the same thing positive, so the total is 0. And of course, this is what the Idaho legislature thinks of teachers, that they stand here and in total do no work. You see, they do -10 up and 10 back, in total no work, so we shouldn't pay. Okay, so anyway, that's just an aside on the concept here of whether this should be thought of as positive or negative, and so it would depend on whether the constant itself is positive or negative. So then, continuing with these, we have all the shore that's going ashore here. So now, having being such a show-off, I have to pick up paper. So got all this out of order now. Now, remember, since all that you have to do is put your name in the left column. You don't have to answer the nosy questions every time, and since you've been here. Okay. We had a lonesome seat today. Going over here. If you look at problem 13, this is another type of problem, and in these 13 and 21 that I have, the differential is part of the volume of material that you're moving, and therefore the differential, instead of being the distance as it was in what we've done so far, is actually appears as part of the force. So what you have is a differential force and then a lift in these pumping problems that would be the distance. As far as how the integral looks, it looks the same as the ones we've been doing. Finally, you have an expression to integrate and either dx or dy or what have you. So with 13, they have a rectangular tank, or maybe you call it a cistern, something like that. The cistern is a big tank that usually holds rainwater. People use to catch rainwater in places in the world where there isn't a lot of groundwater available, such as on an island or something like that. And so this one is 20 feet deep by 12 feet by 10 feet. And I've tried to outline the box there with black. And there's more than one way you can do a lot of the story problems. And I've tried with both the blue and the red to show that there are two ways you could have set this one up. So, first of all, you think of the representative cross-section, which would have water in it. And you see there would be work done if you're taking a slice of water, such as, say, the blue one, and lifting it a distance, say, y, up to the ground level. If you read the story in the book, the ground level is at the top of the system. And they're talking about the work done to pump all of the water up to ground level and presumably out on the grass. And then they're also talking about the work done to lift the top half. In other words, lower the level from clear at the top, which would be 20 feet deep, to this 10 feet. So the differential volume would be the cross-sectional area, 10 by 12. See, it's a rectangle, so that's constant, times whatever be your thickness. So I'm taking the vertical dimension as y. You see, I have two ways I can do it. I can either measure y down from the top, and then my thickness is dy, as I've shown in the blue, or I could think of an origin down here in this corner, more like you would with a three-dimensional coordinate system, and measure y up like that to where the representative slice would be. And then the depth, or the amount you're going to lift the slice, would be 20 minus 1. So like that. Just a minute, I need to drink some water here. So my differential force is density of water. This is back to English units. And in the in the first part of the question, they say to use 62.4, which is a figure normally used for fresh water, although it can vary some, depending on just what the water quality is. That's what they've got into in Flint, Michigan. They changed the source of the water and it actually had different properties and so on. People are very good at outsmarting themselves. Anyway, the differential force is the density times your differential volume. So this is different from what we've been doing in that now the dy is going to be part of the force rather than the force. If you compare with something like this one, where, say, we had the leaky sandbag, this 144 minus 4x was our force, and the dx was the differential in distance that the bag moves. So here, the dy is part of the dv, which, and then the differential work is the differential force times the lift. And our formula for the lift is either going to be the y, if it's the blue setup where you're measuring from the top down, or it's going to be the 20 minus y, if the y is measured from the bottom up, but it doesn't have the dy in it, whichever way you're thinking. So that's what the difference is in these pumping problems as compared to the others. So we must choose our coordinates and our limits so that, limits on y, so that the dy will be positive, so that you get a positive answer. And there are two ways to do this. So your first method is the blue, take the y positive down in the top, and so you're starting then at y equals 0 and working to y equals 20 if it's to empty the whole tank. So our work would be our density, our integral of our differential of work, which would be our lift, which is here, and then the dy is in the expression for the cross-sectional volume. And the density times the 120 dy is the actual differential force then. So you can integrate that, which is pretty easy, and you get about this many foot-pounds of work. The other way you could get the foot-pounds of work is taking positive up from the base, as I've said. Then the origin would be at the base, and then your lift would be 20 minus y, with limits from here up to there. And it will work out to the same number either way. Then, whichever way you came up with this, the B part wants to know how long to empty the tank using a 5/11 horsepower pump. So if you're talking about pumping something, pumping water, it's got to go through a pipe, and there certainly is friction in the pipe. In fact, I think this can be quite important, but they're ignoring that because that's getting off into irrigation engineering or something of that kind. So if you imagine that that's not an issue, and I think in fact it would be, what you're supposed to know is that a horsepower is 550 foot-pounds per second. And so therefore, a 5/11 horsepower would be 5/11 times that. In other words, capable of 250 foot-pounds per second before you consider the frictional loss. So if you divide your total foot-pounds, whichever way you came up with them, by 250, you see you have foot-pounds divided by foot-pounds per second. So working with units is a form of, I admit, a pretty basic form of what people call dimensional analysis, but it's handy in physics, chemistry, engineering, where units matter so much to people, to help you keep your units straight. So if you treated this just like algebra, so you can cancel the foot with foot and pounds with pounds, and then this was in a denominator, so invert and multiply it, you end up with seconds. In other words, you cancel the abbreviation just like you cancel letters in an algebra problem. And it'll give you seconds finally. So it's this many seconds, 5988 about. And then you do the same thing, 60 seconds per minute. So this will give you about 100 minutes. And so if you checked answers with the book says an hour and 40 minutes, which is 100 minutes. So then they're asking you if you want to pump out the top 10 feet, how long will that take? Well, it does not take half the time, you see, because the slice that requires the most work is the very bottom, because that's the last one you can get. and it has to go all 20 feet, essentially. Whereas the very top one hardly goes, is hardly lifted at all. So what turns out to be the case is that it'll not take half the time, it'll only take a quarter of the time. So if you work this over, the only thing you're changing is this upper limit from 20 to 10. And if you work this through, you'll get this many foot-pounds. And again, if you divide that by 250, you'll get this many seconds, which is a quarter of what the time was here. And indeed, if you convert to minutes, this is a quarter of 100 minutes. You see, the way you can see that is your limits, if you set it up this way, then you're taking off the top 10 feet. So your Y is going from 0 down to 10. So you put the 10 there, and where you have the square, with the 20 you had 420 squared. If this were a 10, with 10 squared you'd have 100, and that's a quarter of 400. So if you look at it that way, you know this ought to be a quarter of that. If you're doing the problems in the book, your homework, I said on the syllabus thing, don't do the D part. And the D part is what I call busy work. They have you redo the problem a couple more times with different assumptions on the density. And I think that's kind of busy work to go through the whole thing. What you could do, anybody could do to come up with their answers is say, they give you a different density, find what proportion there is between the density you're supposed to assume and the 62.4, and then multiply all the answers that you got in the parts A, B, and C by that proportion. So if you're thinking the water's lighter and the density is only 99% as much as this, then your answers would only take 99% long, be 99% as much work. So just do the parts A, B, and C. So then let's finish up here by looking at a problem like 21. If you notice in the syllabus, my plan is to have spent today on 6.5 and also to continue with it on Thursday. So there's still more aspects to work problems, but there's really quite a bit to this if you try to think about what you're doing in the physics. So I'm not trying to do everything at once, and I'm also not trying to just leave a lot of it out. What we'll do on Thursday with it is more the force against one side of the dam or a tank from the weight of the water, that type of problem. Well, look at 21. They have a picture of it in the book, if you have the book. So you have a tank or a reservoir which is hemispherical in shape. So this is supposed to be the center of the hemisphere, and the side with the water in it is down in the ground. And we take this as the center then of our coordinate system with an x-axis along here. And because it's sphere, your distance from the center to any point on the edge of it would be the radius. So from here on the slant would be 5 meters, And of course, it would also be five meters like that, and it would be 5 meters here, and it would be 5 meters straight down. So then if you're looking at any representative slice of the water down in here, and of course this could be any fluid that you could pump. It could be liquid chocolate, or it could be oil or gasoline or anything. All that you're changing is what the density would be.
Not mixed together though, right? I'm sorry.
Then you see, you can look for the volume of your slice. It would have a thickness this way, and it would have a radius from the center line, which would be the x. So the x and the distance from the center down to here, which I call y, and the hypotenuse of the right triangle, which would be 5, fit the law of Pythagoras. So notice that your lift from the representative slice in blue up to here would be the absolute value of this distance. If you're taking your origin here and your coordinates in the usual way, then that's x, and then this down below would be negative. So that's why I have the absolute value. The absolute value of a negative number is minus that number, isn't it? The absolute value of minus 2 is minus 2 to get plus 2. So that's why I've said this. So your total lift, you see, the story is you're supposed to be looking at a slice down here and lifting it not just to ground level, like in this problem, but 4 meters above. And so your total lift is the 4, which I have in the red. See, the red's above the origin, plus the absolute value of the distance from where the slice is up to the origin. So 4 plus the absolute value of y, which is 4 minus y, since y is negative. And then the bottom of your tank is at minus 5 meters down. The top slice would be up here at y equals 0. Your slices don't go all the way up to there. They all get lifted to the ground and then up 4 more meters. So that means the limits on your integral are going to be minus 5 to 0. So back to your hemisphere, you see your equation would be for the law of Pythagoras, that x squared plus y squared is 5 squared. And it doesn't matter on the y whether it's positive or negative, because minus y times minus y is still y squared. So you can say this relationship for the slice that's down here, and therefore that x is the square root. Actually, you're going to use x squared, so it's really x squared is 25 minus y squared that you'll use. So then we're working with metric units. They tell you that the density for water is 9,800 newtons per cubic meter. And so your differential volume is the area around a representative slice, which is pi x squared, where you can replace the x squared from here. And then the dy is the thickness. And so you have pi times 25 minus y squared dy. So your work would be the 9800 times the pi, which is a constant. And then if you're setting things up as I have been, working from here down, your very bottom slice is at y equals minus 5, and your top slice is at y equals 0. And your lift is 4 minus y. Remember, the y is negative, so altogether this would be a positive number. And the differential volume, which would be this part. So I'd multiply this out, FOIL. So first, then the outside would be there, then the inside would be that one, and then the last would be that product. Minus times minus would be plus. And you integrate term by term and put in your limits, and you'll get so many joules. Now, the other way you could do this would be to take y positive down instead of negative down, and if you did that, you see then you'd be going, if you're working positive down, then instead of working bottom to top so that dy is positive, you'd work top to bottom, so your limits would be 0 to 5, and then if y is positive down, your lift is y plus 4, you wouldn't have the absolute value. This part would be the same. The law of Pythagoras is what it is. Square plus square equals square. So that's the same. And your dy would still be positive because positive down you're going from smaller to larger. So what you have to do in whichever method you're using is choose your limits so that as you go from your starting to your ending position, your dy would be positive, so that you get a positive answer. And this ought to give the same answer that does. So you want to pay particular attention to this type of problem, because you might see one on the test that I'll be handing out next week. If you have looked at your syllabus, next Thursday I'll hand out the first test, which you have a week to do. A week or a week and a day. The following week I don't care whether you turn it in on Thursday or turn it in on Friday, because I won't grade them until the weekend anyway. Well, we'll continue with these problems in section 6.5 on Thursday, and probably start 6.6, which we'll work with more on Friday. So if you're not flying to Washington, D.C. in that area, be grateful, because it sounds as if people are going to have a very hard time with all the snow they're predicting. So be glad you're here. Have a good week.